To another select seminar. Today we have Pranay Gorantla, who will be talking to us about tensor networks for non-invertible symmetries in 3+1 dimensions and beyond. So please, Pranay, start.
Thanks, John. Thanks for this invitation. I'm really excited to be here. So this talk is based on some work that I did with Shuheng and Nat. And depending on how this talk goes and how the time works, I might even mention a few more results in a very closely related work with Jimmy. A big picture here is my work is mostly focused on generalized symmetries, like generalized notion of what a symmetry is in physics. There have been many advancements in the recent years, and these things have had impacts on various areas in physics and also in math. And in fact, there are two science collaborations that are currently actively working on the implications of generalized symmetries in quantum field theory, condensed matter, quantum information, mathematics, etc. And I've been a part of both these collaborations. I'm still a part of the global categorical symmetries collaboration right now. So let's get into the talk. You can see my cursor, right, when I'm moving it. Are you able to see the cursor?
Yeah.
Okay, sounds good. So in the modern perspective, the generalization of global symmetry that I've been talking about is they're thought of as topological operators or defects in a relativistic quantum field theory. These include examples like higher form symmetries, non-invertible symmetries, and higher group, and so on. Like there are many fancy terms for these. And recently, these generalizations have been explored on the lattice in the Hamiltonian picture, with the natural setting as a tensor product Hilbert space. And one of the simple examples uh, uh, of such of these kind of generalized symmetries is a famous one-year duality in 1+1D transverse field Ising. This is like as simple as you can get. This is like a textbook example, and we're still finding new stuff in it. So let me go to transverse field Ising model and explain where this comes from. So the setting is a periodic lattice, one-dimensional periodic lattice with L sides, and you have a qubit at each side. And the Hamiltonian is the Ising Hamiltonian, where the first term here is the Ising interaction, where you have product of two z's on the nearest neighbor sides. And the second term is the transverse field term, where you have a poly x operator at every side. The z and x are the poly z and poly x operators. Now, this Hamiltonian has two usual standard symmetries that we all know of. These are invertible, and there's nothing non-trivial about these. The first one is the Z2 spin flip symmetry, which the operator that generates this symmetry is the product of all x. Basically, it acts on every qubit by flipping the spin, so 0 to 1 and 1 to 0 at the same time on all the sides. And it's a Z2 symmetry because it squares to 1. The operator that generates it squares to 1. There is also a translation symmetry that's evident from from the way I wrote this Hamiltonian, which shifts a qubit to the next side. Okay, these are invertible symmetries. These are well understood. The phase diagram of the Ising model is also well understood. Onsager solved it long ago in the classical StatMech kind of setting, but we also know exactly how to solve it even in the Hamiltonian formulation. At small h, the C2 symmetry is spontaneously broken. We are in a ferromagnetic phase where the spins try to align with each other. So there are two ground states, one where all the spins are 0, the other where all the spins are 1. When h is very large, the Z2 symmetry is not broken, it's preserved, and there's a unique ground state. All the spins try to align in the direction of the field, so they're all in the plus point. So here 0 and 1 are the eigenstates of the poly Z matrix, and plus and minus are the eigenstates of the poly X matrix. And these two phases are separated by a second order transition, which is described by the Ising CFT. And that happens exactly at h equal to 1. The reason for this was already known even before this model was solved. This is because of Kramer's one-year duality, which in the Hamiltonian picture exchanges is the Ising term and the transverse field term. Under this exchange, the parameter h in the Hamiltonian is mapped to 1 over h. So these two phases are exchanged under this duality transformation. So for generic values of h, this duality transformation, although looks a bit like symmetry, is not actually a symmetry because it doesn't commute with the Hamiltonian. It gives you a new Hamiltonian by this transformation. But at h equal to 1, the model is self-here. And so there is a chance that this is actually a symmetry. But from our first year of grad school, or maybe even in undergrad, we learn that symmetries are usually captured by unitary operators in quantum mechanics. So let's wonder if there is a unitary transformation that does this transformation. We immediately see a contradiction because when we act by this symmetry with this duality transformation on the Z2 symmetry operator eta, we end up with this result here. So we have the product of x, and the action of u on x by this transformation is zz. So you have a product of all pairs of zz. And because z square is 1, these things cancel out with each other, and you end up with the identity operator. But this doesn't make sense. If u were unitary, what this implies is eta equal to 1. But there are clearly states in the spectrum which are z2 odd. They're not z2 even, where eta is equal to -1. So this result doesn't make sense. So what gives? So the resolution for this is that we should think of this duality symmetry as a non-invertible symmetry. It doesn't have an inverse. It works non-trivially only on Z2 even states, but it annihilates all Z2 odd states. Now, this thing was analyzed already in the continuum very long ago, and not too long ago, it was also understood in the Euclidean lattice. But today, I want to talk about this non-invertible symmetry on the lattice in the Hamiltonian formulation. So there is an explicit expression for the non-invertible operator that generates this duality symmetry in the literature. It has the following structure. There is this pink stuff, which is a product of unitary matrices. So the whole thing is a unitary matrix. In fact, this product here has a sequential quantum circuit interpretation where there is a unitary that acts on two sides and then another unitary that acts on the next two sides and so on. But that's not the whole story. We also have to multiply it with the projection onto the Z2 given state. This is what makes this operator non-invertible. And one can also work out the algebra of this operator and verify some things. For example, it does what we expect it to do. It maps x to zz and zz to x. It absorbs the Z2 symmetry operator, it commutes with the translation, and its fusion rule with itself, that is d square, is 1 plus eta times t. Now, I'm not sure if anyone here is familiar with the continuum version of this story. In the continuum, d is an internal symmetry and it doesn't mix, there is no t on the right-hand side. It's just 1 plus eta. So this translation here is a new feature on the lattice. And this is unavoidable. Whenever you're talking about duality in this model on the lattice, it's you cannot avoid the appearance of this by redefining d. But the question that I want to ask is like, where did this expression come from? And how do you evaluate this algebra? Like, is there a simple intuitive way to see this? And there are many examples of duality symmetries that we now know that are represented in higher dimension, like in 2+1D, 3+1D, and so on. How do we come up with expressions like this for these symmetries for in higher dimensions and beyond? None of this is obvious. In fact, the way this was derived in this particular case was that was using Jordan-Wigner transformation to transform the Ising model into free Majorana chain and then do everything there. Everything becomes very simple in that language. But such a construction, such a Jordan-Wigner transformation doesn't exist in general dimensions and doesn't always work for arbitrary models. So we really need to find a different representation of this operator that's more convenient to work with, that can be easily generalized to higher dimensions. And that's the aim of this talk in providing a different representation, and that's the tensor network representation of the duality operator. In particular, it's a matrix product operator. That's what I'm trying to get at. So here I'm already showing the ZX diagram of this matrix product version of the non-invertible operator. The first thing that you can already notice from this diagram is that it's manifestly invariant under translation. There is this common motif that's repeated for every site in a periodic way. Notice that I use the vertical direction for space and horizontal direction for time. So this is manifestly invariant under translations, which is a nice thing, which wasn't obvious in the previous representation. Also, this is easier to generalize to higher dimensions and also beyond. In fact, in this talk, I'll talk about the 3+1D generalization called Wegner duality, and also about dualities in generalized Ising models on graphs. And finally, what makes all of this very easy to work with is ZX calculus. And so that's what I'm going to talk about today. I'll briefly, very quickly review ZX calculus, and then use this framework to construct and derive the algebras of various duality operators in 1+1D, 2+1D, and on graph. And depending on how much time we have, I'll also talk about some of the consequences of these duality symmetries in physics. Any questions at this point?
Can I
Okay.
just, you mentioned two cases where Z2 symmetry is broken and one where it's not broken. Like, can you explain what it means for the symmetry be broken or not broken?
Okay. So you're talking about this, right?
Yeah.
So when we say the symmetry is spontaneously broken, what it means is the symmetry commutes with the Hamiltonian. That's always the case because the symmetry has to be there in the system. But the ground states don't respect that symmetry. In fact, if you act with the product of all x on this state here, all zero state, it gives you the all one state. It flips all these spins and gives you this one. So it doesn't act trivially on the ground states. It permutes the ground states in some way. It acts non-trivially on the grounds. That's what I mean by the ground states breaking, spontaneously breaking the symmetry.
That makes sense. Thank you.
Yeah. Any other questions? Okay, so let me quickly review ZX calculus. So I'm gonna apologize for anyone that I'm not citing here. I'm just citing John's review on ZX calculus because that's where I learned most of this stuff. But okay, let me start with that. So the fundamental object in ZX calculus is a ZX diagram, which is a graphical representation of a linear map between qubits. And the three most fundamental generators in this context are the two spiders, the Z spider and the X spider, and the Hadamard box, the H box. Now, I'm guessing all the audience here are familiar with this, with these definitions. So let me quickly give some examples. The green spider with a phase of pi and one input and one output is a poly Z operator. And if the color is red, then it's a poly X operator. And then these are the eigenstates of the poly Z and poly X operators. And as is convention, I omit the phase if it's a multiple of 2 pi. And I've learned this useful mnemonic whenever I forget which one is a Z or which one is the X spider. The GHZ state is the all zero plus all one state, and that's represented as a green G for G, G for green, and G for G at Z. So that's one way to remember which one is the Z spider if you're ever confused. There are also other generators, the identity, the swap gate, and the bell state, and the two bell states, the cut and the brown versions. Now, these are all the generators. You can construct more complicated linear operators, more complicated ZX diagrams by combining these generators in a nice way. The red dashed line is just as a guiding tool. Like I'm not going to use it in much of the later talk. What this means is you take two diagrams, if you put them next to each other, that's like taking the tensor product. Similarly, here we have a tensor product, and we glue the wires together. That's like taking the product of the linear maps or the composition of the linear. And this, in this specific example, this kind of gluing things gives us the C-norm gate. And one of the important things about ZX diagrams is that their only topology of the diagram matters as long as you keep the inputs and outputs fixed. And that can be seen, for example, in the C0 gate in this way. You can either define it this way or this way, it doesn't matter, they represent the same linear map. So it's commonly written in this way. But there are also topologically inequivalent diagrams that represent the same linear map. For example, all these three non-trivial diagrams here, they're all the identity operator. So there are lots of relations between these generators. So one might ask if we can ever like relate two ZX diagrams that correspond to the same linear map. And indeed, there is a complete set of rewrite tools. I'm not showing all of them here, but only the ones that I'm going to use in this talk. I show 9 of them here. I think these are the most commonly cited rules. And I'm guessing that the audience is already familiar with this rule, so I'm not going to say much about this. So let's use this technology now to analyze and define duality operators in various dimensions. Just as a warm-up example, let's go back to the usual invertible symmetries in a 1+1D Ising model. The Z2 symmetry is generated by eta, which is a product of X. And that can be written as the product of all red spiders with a pi phase in them. And this is a common notational device that I've seen in papers on CX calculus. This is the annotated bang box, where I runs from 1 to L. It basically labels all the sites or all the qubits. And eta square can be computed very easily. It's just identity that's easy to see using spider fusion and identity rule. The translation symmetry can be represented as this ZX diagram here. Now, this may not seem like we are using the generators, the actual generators that I mentioned before, but you can write this in terms of product of swap gates between neighboring subs. And here I introduce a slightly different, slightly generalized notion of bang box, where I replace the top and bottom lines with dashed lines. What this means is any wire that ends on this dash line is continued periodically in the other direction, so it comes out here. So how many ever lines you have that end here, you should have the same number of lines here. And they should be ordered in the correct way. So in this particular example, you take this motif and repeat it periodically in the vertical direction. Just to see that this is indeed the translation operator, let's take, for example, L equal to 3 and calculate T cube using the ZX calculus. I color the wires differently so that you can see that you can deform them into the identity. Okay. So next, let's talk about the duality operator. The ZX diagram for this is this one here. And using the periodic bang box notation, we can write it like this. So this is the MPO tensor. If you're more familiar with the matrix product operator technology, this would be the MPO tensor that's repeated periodically in the spatial direction. Let me give you some motivation for where this diagram came from. In the continuum, in the literature, famous one-way duality and other duality symmetries are understood as gauging the Z2 symmetries, the internal Z2 symmetries. And on the lattice, when the gauging is performed by a map from the Hilbert space on the sides to Hilbert space on the links. Now, let me explain this, why this happens, why this change of Hilbert space happens. When you want to gauge the Ising model, you introduce gauge fields on the links. This is how you would normally do it on the lattice. You have some matter fields on the sides, and when you want to gauge it, you couple it to gauge fields on the links. And in this case, because it's a Z2 symmetry, the gauge fields are themselves qubits. So you have Z hat and X hat on the links. And then you impose Gauss law constraints and do gauge fixing. And at the end of which, you end up with a Hamiltonian for the gauged model, where the qubits now live on the links. So these gauging maps, which were defined already in the literature, take you from act on the Hilbert space on the sides, and the output is on the Hilbert space on the links. So this is not good enough for us because we are interested in constructing an operator that acts on the Hilbert space on the sides. It should be a symmetry that commutes with the Hamiltonian and takes you back to the Hilbert space on the sides. But what this map does here is take you from the sides to links. To account for this, we also compose with a half translation, which maps the sides back, which maps the links back to the sides. And indeed, if you push this gauged Hamiltonian through this half translation, you end up with the famous one-year dual Hamiltonian with the parameter 1 over h in the case of the Ising model. So this tells us that the duality operator is a composition of gauging times a half translation. That explains why we have a bend here. Originally, you had a map from sides to links, and we bend the links back to sides. This here is a ZX diagram of a half translation. We can straighten this out by making it horizontal by pushing all these things here. Oh, sorry, all these diagrams here down by pushing them down. But that creates a bend here. And this is a half translation before doing the gauging. So what this tells us is that you can either do half translation and then do the gauging, or you can do the gauging and then the half translation. You end up with the same operator. These two operations commute. Also, there is a counterpart of this half translation where which takes you from sides to the links. And when you compose these two different half translations, that gives you the full unit translation from a side to the next side. Okay, now that we know what the operator is, let's whether you are familiar with this gauging picture or not, let's just take the diagram for granted and see that it does exactly what we expect it to do. And the first test would be verifying whether it does the Kramer's one-year transformation. And for that, let's compute d times x. So you push a red spider with a phase of pi into the ZX diagram for d. Using the pi commutation rule, it splits into two pi's when it passes through this green dot. And then it changes its color when it passes through this Hadamard up here, and this when it goes down here. So you end up with this diagram. And then you can use the spider fusion rule to take this pi out here onto this line, and similarly this pi onto this line. And that's how you end up with ZZ times D. So this does exactly what we expect it to do. It takes X and spits out ZZ. And you can also verify that if you send in product of two Z's, you end up with a single X on the other side. More generally, if you take a product of X on some bunch of consecutive sites and push it through the D, you end up with product of Z at the endpoints of this interval. Now, this is the lattice analog of this famous continuum picture where you have two order operators in the Ising CFT and you sweep this duality defect across these order operators. You end up with two disorder operators connected by a Z2 symmetry line, the eta line. Now, you may not, I'm not sure if you're familiar with this picture, but this is exactly the continuum analog of whatever I showed here. You can see the resemblance almost. The left-hand side here corresponds to the right-hand side here, and the right-hand side here corresponds to the left-hand side here. This is like a one-to-one map between the continuum and the lattice. We can also compute the fusion of D with itself. It's slightly more involved, so let's do this in steps. First, we compose D with itself, so that's this ZX diagram. And I want to make this bend in the middle horizontal. That makes this bend even worse. Like it takes it up here and down here. And you might remember that this is exactly the ZX diagram for the translation. So what we did here is pull out a factor of translation times product of the two gauging maps that I showed before. So you already see that there is a translation involved in this fusion rule. All we now need to compute is the product of these two gauging maps. That can be done again using the calculus in like 5 or 6 simple steps. First, we have this ZX diagram. We push these two Hadamards up, and through this periodic boundary, they come back here and cancel with these Hadamards, but we end up with these color changed spiders. Then we fuse these two spiders horizontally and split them vertically and push one of the vertical spiders up here so that you end up here. And this is a familiar configuration. This is the left-hand side of the bialgebra rule. So you apply bialgebra and replace it with this ZX diagram. And now this green spider is connected to all the other green spiders in a periodic way. So you can fuse all of them together and pull it out. At the end, you end up with this diagram more explicitly. And let me call this C. And in the next slide, I'll show how to simplify this further.
So we can split the step where you went from the chain to 1Z spider?
From here?
Yeah, from here to the next
step. So this green spider is connected to green spider up here in the next copy, and so on in the next copy. They're all connected because of these wires. So you can use the spider fusion to fuse all of them together.
But you still have the wire, right? You can fuse all of them, but the
These
wires.
wires, yeah. In fact, that single that single green spider is connected to all the red spiders, and that's what I'm showing here. These wires are all still there.
I guess what I'm not following is that you can fuse all the ones that are like on the top and bottom, but like, oh, is this like periodic boundary? So it like
Yeah.
it
It
fuses.
is periodic.
Okay, I see. Thank you.
Yeah. So
So
it is periodic.
Pranay, this notation you have for the box, is this like did you formally define it in some way, or is this like a shorthand that you're sort of using in this paper? Like it's not like a bang box or anything like
It's
we're
not like
talking.
bandbox. It's like a periodic version of bandbox where whenever a wire ends here, it should be connected to the bottom wire in the next
Yeah,
copy. So you
yeah.
repeat this and then you glue everything together periodically in the finally.
So in principle, you could, I guess you could view this as being indexed by a graph or something that like each of these things corresponds to, um, or maybe like a two-array graph where like each top thing goes into the next things connected on the graph or something. I mean, it's trying to see um, because like it's now for this periodic boundary conditions where it's like a loop. I can see how this works, but I'm wondering if you want to do this more generally. Like, is there a way to still write this in some way? If you have,
Oh,
say, multiple wires going up or down?
I think so. I think so. Like, in fact, later on when I talk about the 3+1D, this won't be enough. Like, I have three dimensions and like, three things going in three periodic directions. And I don't have a bang box notation for that, but I just showed it's hard to come up with those things. It's a four-dimensional diagram, but the idea can be generalized to other things. Yes.
I see that Neil has raised his hand.
Yeah, I guess I was going to comment mostly what Pranay remarked. Because it's so simple, you could get away with a single diagram like this. Maybe if you have a Cayley graph more generally, you could get away with something that is very, very slightly more information than this. For a more general graph, you'd probably need to add a lot more structure.
That's right. That's right. I agree with you. Yeah. Like in all the examples that I'm going to talk about, I'll have some periodic boundary conditions, so it's actually easy to see what I mean. So I didn't actually define this formally, but I kind of know what's happening here. But if you want to extend this to general graphs, I don't know how to do this, but I think there should be some way of doing it.
Yeah, the notation also reminds me of these stream diagrams that I think Titouan Carret and other people have defined, where you have like a process and it outputs something and this is fed into the next stage of the process. But then they don't
Yeah,
consider periodic ones; they consider like infinite.
yeah. So when you say something like that, it feels like that's in the direction of time, but
Yeah,
here this is the direction of space,
yeah, yeah.
the vertical direction. So that's one difference. But yeah, I agree with you.
Thanks.
Yeah. So thanks for the questions. So then let me continue with simplifying this diagram further. I have this diagram here from the last slide. I split this green spider into L plus two green spiders in this way. That's just spider fusion. This makes it very recognizable. I think of this top line as some auxiliary qubit called A. We can recognize C0 gates here. There are L of them, where the control qubit is always this A, and the target qubits are the L qubits. And then we are taking the partial matrix element in the plus plus states of this auxiliary qubit. So that's this expression here. And using the definition of the C0 gate, it's very simple to like compute this partial matrix element. It turns out to be 1 plus eta. This is exactly as I promised. D square is t times 1 plus eta, where this t was obtained in the first step in the last slide. And the 1 plus eta comes from the product of the two gauging maps. So let's summarize what we have so far. We have the Z2 symmetry operator, which squares to 1. We have a translation whose L power is 1, and the commute with each other, obviously. And the D, the Kramer-Sonnier duality symmetry operator, it absorbs the Z2 symmetry operator, and it's manifestly invariant under translations. So it commutes to the translations, and it squares to T times 1 plus eta. Now, this name C that I introduced, this letter C, it's because in higher dimensional analogs of this algebra, the right-hand side here, where you sum over all possible internal Z2 symmetry operators, is called a condensation operator or condensation defect, and that's why I'm using the letter C here. And the condensation operator also commutes with translation. That's obvious from this diagram here. Okay.
Sorry, Pranay, can I?
Yes.
So
Yes.
eta in this case is like a product of Pauli x's.
Yes.
So okay, so then 1 plus eta is exactly the projector onto the +1 eigenspace of the Pauli x's.
Yes. Yes.
Okay. Right. So it's saying it's commuting with a certain Pauli. Right. Okay.
Yes.
Yeah. Yeah, because this diagram you had on the previous slide with all the x's connected to a z, like this diagram, we know from a quantum error correction, like this represents the stabilizer for like a certain Pauli. Like you see these kind of diagrams where you write down error correcting codes in
yeah.
ZX
Yeah.
diagrams.
In fact, in your review, I've seen this kind of diagram with a phase alpha here. Yeah, but okay, yeah. But I found this more convenient, like because the end result is 1 plus eta, and that's what we are trying to get. Yeah, I was wondering how to derive this, and then I realized I can split it into C nodes in this way.
There is actually also a neat way to derive this in a different way, which is in a book. I can send you a reference if you want. I think it's slightly more direct proof than what you have.
Oh, thanks. That would be great. I'd like to know. Yeah, thanks a lot. Okay. Now that the 1 plus 1D story is none, I'm going to move on to the 3 plus 1D story. Any more questions at this point? Okay. So the 3 plus 1D story is kind of very similar. In this case, the simplest lattice model that realizes the duality symmetry is the Z2 lattice gauge theory in 3 plus 1D. And the setting here is a periodic cubic lattice where the qubits now live on the links, not on the sides, they live on the links. So these are like the gauge fields on the links. And the Hamiltonian has two terms once again. The first term is a product of the poly Z operators on the links around the plaquette, and we sum over all the plaquettes. And the second term is a poly X operator, sum over all the poly X operators on the link. In the literature, this first term is also known as a magnetic flux term, and the second term is known as an electric field term. Like if you take a continuum limit of this and a leading order, that's what you get. You get a B square kind of term and a E square kind of term. Because this is a gauge theory, you also have to impose a Gauss law. In this case, at every site, we take the product of all the poly X on the links surrounding that site and equate that product to 1. That's the constraint that we impose. This is the Gauss law constraint. So we are looking at a subspace of the total tensor product Hilbert space. This subspace doesn't have a tensor product structure because of these Gauss law operators, but that's okay. That's what is common in gauge theory anyway. This model also has some usual invertible symmetries. There is a Z2 one-form symmetry, which is generated by these operators. So given any surface, dual surface on the dual lattice, the symmetry operator is defined as the product of all the poly X's on the links that pierce that dual surface. It's easy to check that this operator commutes with all the terms in Hamiltonian. This generates a Z2 one-form symmetry. And the Hamiltonian is also manifestly invariant under translations and rotations, the way it's written. Like I'm showing one orientation of plaquette and one orientation of link here, but I'm adding all possible orientations. So it's invariant under translations and rotation. Now the phase diagram of this model is pretty hard to compute. Like this model is cannot be solved analytically, unlike the Ising model. There is no free fermion representation of this model, but people have done numerics back in the 80s, and we know numerically what the phase diagram should look like. At small h, there is a Higgs phase where a large Wilson loop obeys a perimeter law. But in a modern understanding, one can think of this as the Z2 one-form symmetry being spontaneously broken. And similarly, at large h, there is a confining phase where the Wilson loop obeys an area law. And in the modern language, this translates to the Z2 one-form symmetry being preserved. And the transition between these two phases is first order. So it's a gap point. It's not described by a CFT. It's actually captured by a TQFT. And it occurs exactly at h equal to 1. Once again, there is a duality reason for this. Wegner first observed this back in 60s, I think. where x and the product of z term are exchanged in a Hamiltonian manner. Under this exchange, once again, h is mapped to 1 over h. So at generic values of h, this is not a symmetry, but at h equal to 1, the model is self-dual, and this is indeed a symmetry. Once again, this cannot be generated by a unitary operator, the symmetry. It's a non-invertible symmetry. And this was, in fact, one of the first examples of non-invertible symmetries in higher dimensions, in particular in 3+1 dimension. That was analyzed only in 2021, like 4 years ago. And then later it was also analyzed on the Euclidean lattice. Now I want to talk about the Hamiltonian version of that. Once again, there is a ZX diagram way of thinking about it. And the common mantra here is the same. Any duality symmetry can be thought of as gauging, but on the lattice, there is an additional subtlety of half translation. So the gauging map in this case is described by these ZX diagrams. Because I'm not an expert in drawing 4D figures in 2D, my way out is this. I use arrows to represent the flow of time. So the inputs are in the links here, and the outputs are in the plaquettes. Here, I use these thick gray lines to represent the links of the cube equators. So 3 links meet here at a side, and these 3 things here are plaquettes. So I have green spiders on all the links and all the plaquettes, and there are Hadamards connecting neighboring plaquette and links. So this is the structure of the ZX diagram for the gauging map. Now, this is to be expected if you're familiar with gauging higher form symmetries. What we have here is a one form symmetry. So you can think of this as matter fields living on the links. And the corresponding gauge field is a two form symmetry, which naturally lives on a plaquette. And that's why the output is on a plaquette. But this is not good enough for us. This is a map from links to plaquettes. We want an operator that acts only on the links. So we again compose it with a half translation that takes you back from plaquettes to links. And this half translation can be thought of as translation by half. You can do a gauging followed by half translation, or a half translation followed by gauging, just like in 1+1D. And 2 such half translations composed to give a full translation in the 1-1-1 direction. So this is the definition of the Wegner duality operator. Now let's see how this acts on the rest of the operators in the model. Using ZX calculus.
Can I ask a question about the
Yes.
diagram here? Should
Yes.
you have another Z spider where the gray lines intersect and the Hadamard?
Here?
Yeah, should you have an edge between that and all of the Z spiders?
No.
So it's
This
not
is the full diagram.
not like a cube.
Oh yeah, this diagram, the ZX diagram itself is not a cube. You have Z spiders only on the links and plaquettes.
Okay.
Yeah. Any other questions about this diagram? Okay. So the duality operator using ZX calculus, you can show that it maps the poly X operator on a link to product of poly Z operators on the plaquette that's half translated from this link. And similarly, it maps product of Z on a plaquette to a poly X operator on the link that's half translated from the plaquette. You can also use these relations to show that the duality operator maps a Wilson loop, which is the product of Z around a curve, to an open Z2 one-form symmetry operator. It's an open surface with a boundary shown using this dashed line here. It's basically the product of all x's along a surface bounded by this boundary. And this is the lattice analog of this continuum figure, where if you have a Wilson loop and sweep a duality operator through this thing, on the other side, you end up with an open Z2 one-form symmetry operator. We can also compute d squared using ZX calculus. As usual, the first step is to pull out this factor of translation in the 1-1-1 direction. And then all we need to compute is the product of the two gauging maps. This is more involved than in 1+1D, but it can be done quite easily. And the end result is you end up with this kind of an operator. Now, this may not seem as like any simple, but one can again use the same technique that I used before in terms of writing it as a product of C naughts and taking partial matrix elements, and show that this operator is a sum of all the one-form symmetry operators, the Z2 one-form symmetry operators, up to some scale factor. In that sense, this is also again the condensation operator. And in fact, this is the lattice analog of this continuum result, that the square of the duality defect is the condensation defect. Now, there is a nicer and simpler form of the condensation operator. You can write this sum here as product of these three operators times the projection onto the Gauss law preserving states. Now, these eta xy, yz, and zx are the one-form symmetry operators on the xy, yz, and zx planes. These are the three non-trivial, non-contractible surfaces on a three torus. Because of the periodic boundary conditions, my spatial manifold is like a three torus. And these are the three non-contractible surfaces. And because I'm imposing Gauss law explicitly, this projection acts like an identity operator, so we can ignore this. So the condensation operator is essentially this. And this matches exactly with the continuum result, where once again, you have sum over all the one-form symmetry operators on all the non-contractible, like non-trivial homology, the second homology classes. And these are precisely the three non-contractible surfaces. So you have 8 terms here, and you also have 8 terms here. And the factor in the denominator also matches. One can compute that this zeroth cohomology group is Z2. So it has 2 elements, and that's the factor of 2 here. So both the continuum and lattice results match exactly. So here's the summary of all the operators. We have a Z2 one-form symmetry operator that squares to 1. And it's absorbed by the Wegner duality operator. The Wegner duality operator squares to the translation in 1-1-1 direction times a condensation operator, which is the sum of all one-form symmetry operators. Now C commutes, the condensation operator commutes with both translations and rotations. This is evident from its ZX diagram. But the duality operator commutes only with half translation, only with the translations. It doesn't commute with rotation. In fact, there's a nice feature here. When you act by a rotation on the duality operator, you end up with a different duality operator whose square involves translation in the rotated direction, where epsilon here is a rotated version of 1-1-1. So there are several different, in fact, 8 different duality operators here associated with each of the rotations. And they generate all these different 8 duality operators, which are all equally good. But one non-trivial fact for all of these is that we cannot get rid of this translation. That's the non-trivial fact here. So let me now quickly go through duality on the graphs. So the setting here is a bipartite graph. This is like a generalization of whatever I've said before. The setting is a bipartite graph where you have 2 vertex sets, one on the qubits and one which is associated with the qubits that you have in the problem, and the other set of vertices which is associated with interactions in the problem. Now, this bipartite graph has an associated biadjacency matrix, which tells you which is 1 if V and V hat have an edge between them, and 0 if not. If you're familiar with LDPC codes in the quantum information context, this bipartite graph is known as a Turner graph, and the sigma matrix is known as a parity check matrix. Given this graph, one can write down a Hamiltonian of this type. The first term is like a generalized version of the Ising interaction, where you take a interaction vertex and look at all the qubits that are adjacent to it and take the product of poly Z operators for those qubits. And the second term is just sum over all the x on the qubits. This model again has a Z2 symmetry generated by product of x with appropriate powers A, where these A are binary 0-1 matrices that are in the kernel of this matrix sigma. Just to orient ourselves, like understand what this abstract stuff means, here's the example of the Ising model. In this case, the graph is a cyclic graph, where the black dots are the sites and the hollow dots are the links. They correspond to the interaction between nearest neighbor sites. And the matrix sigma has this structure, and it has a kernel generated by a single vector, the all-ones vector. And that's precisely the product of all poly X operators. That's the Z2 symmetry associated with this vector. Now, what about the spatial symmetries and duality symmetries? These are related to the automorphisms of the graph. So given in a graph, automorphism is defined as a map from the vertex set to itself, where if two vertices are adjacent, then their images under this map are also adjacent, if and only. In the case of bipartite graph, there are two kinds of automorphism. One is a preserving automorphism, which preserves the left vertex set and the right vertex set. And in the case of this generalized Ising model, this corresponds to spatial symmetries such as translations and rotations. There are also reversing automorphism, which exchange the two vertex sets. And one necessary condition for this, for the existence of a reversing automorphism, is that you should have the same number of vertices in both left and right vertexes. But this is not sufficient. You need more. There are more conditions needed. But as an example, again, we can look at Ising model. So this pi here, this preserving automorphism corresponds to the unit translation, whereas this reversing automorphism, which maps black to hollow and hollow to black vertices, corresponds to the half translation that I was talking about. There are also other automorphisms associated with reflections or parity symmetry, where this one here, for example, is a preserving automorphism because it maps black to black and hollow to hollow. Whereas this one here maps black to hollow and vice versa. So this is a reversing automorphism. Now let me explain how a reversing automorphism corresponds to a duality. As before, the mantra is again the same. Duality should be thought of as gauging the Z2 symmetry. Plus, in this case, the subtlety is the reversing automorphism. And in fact, the gauging map is very closely related to the bipartite graph that we started with. You simply take the bipartite graph, replace all the solid vertices, the black vertices with green spiders, all the hollow vertices with red spiders, and join them using wires, add input and output legs, and put Hadamard boxes on the output end. You could also move all these Hadamards to all the edges here and make every vertex green and have Hadamard edges here. But putting Hadamard boxes here is cumbersome, so I'm not going to do that. There is also corresponding dual gauging map, which is just simply a reflection of this. Now, if B and B don't have the same number of vertices, or if the bipartite graph has no reversing automorphism, there's nothing more you can do. But if it does have a reversing automorphism, you can compose that with this map to construct an operator that acts on the Hilbert space on the qubits. And two such reversing automorphisms can be composed to give a preserving automorphism associated with a spatial symmetry. So here's the bottom line. Here's the algebra of the operators. This duality operator constructed using the reversing automorphism exchanges the transverse field term and the generalized Ising term as dictated by the reversing automorphism. And the symmetry operators also have like very nice fusion rules. The internal symmetries are labeled by the vectors in the kernel, and they have an abelian fusion rule. The spatial symmetries are labeled by preserving automorphisms, and they also have abelian fusion rule. The duality operators, on the other hand, they are labeled by the reversing automorphisms, and they have this kind of a non-standard fusion rule, where you have a spatial symmetry associated with a composition of two reversing automorphisms, and a sum over all the Z2 symmetries. So this is the analog of the condensation operator. More importantly, when rho is equal to rho prime, and if rho square is equal to 1, we don't have any spatial symmetry on the right-hand side. So the duality operator does not mix with spatial symmetries, if and only if rho is a involution, reversing involution. Now, does this ever happen? In fact, I've given you an example in the previous slide. This reflection that generates a reversing automorphism is actually an involution, because if you apply it again, you go back to the original graph. And this generates a non-invertible duality operator associated with the reflections that does not square to some translation. It does not mix with any translation. And there are many other examples that you can construct in 1+1D or in 2+1D And even the 3+1D Z2H theory I talked about can be fit into this framework of all the graphs. Okay. So I think I'm like getting close to the time. So let me very briefly mention some of the consequences of non-invertible symmetries. One of the important questions in physics is understanding the low energy phase of a lattice model. And there are three possibilities in general. One is that you have a non-degenerate ground state and there is a non-zero gap in the thermodynamic limit to the rest of the states in the spectrum. Or the ground state could be part of a gapless spectrum, that could be a band or something. Or the ground state, there could be multiple degenerate ground states and with a gap to the rest of the spectrum. These are three generic possibilities that you can have in the low energy phase of a model. But when you have a duality symmetry, for example, the 3+1D or the Wegner duality symmetry, this first possibility is ruled out. You cannot have a trivially gap phase in a model that has a duality symmetry. But you can have both gapless and gap with degeneracy, and there are, in fact, examples of these. I already mentioned the Ising CFT in the Ising model at the transition point. That's a gapless point. And in 3+1D, for example, you can have the Maxwell theory at a particular value of coupling, and it has a Wegner duality symmetry at that point. For the gap examples, in the 3+1D, I've already mentioned the first order transition point in the lattice Z2H theory. So that's an example of gap phase with non-trivial degeneracy. In the Ising model, there is no gap phase within the usual Ising model, but there is a deformation, some higher order terms that you can add, after which you can reach a point where it's gapped and has non-trivial degeneration. So in the interest of time, I'm going to skip the next few slides and summarize my work quickly. So I've talked about tensor network formalism for non-invertible symmetries. It's very convenient because it makes the invariance and the translation symmetry manifest. It's also easier to generalize to higher dimensions and also models on arbitrary graphs, as I demonstrated. And much of the simplicity in this calculation follows from a powerful graphical language called ZX calculus. And I demonstrated all of this in the case of 3+1A duality in 1+1D, or Wegner duality in 3+1D, and dualities on graphs based on bipartite graphs. And I've also talked about a necessary and sufficient condition for when this duality symmetry mixes with a lattice translation or a spatial symmetry in general. I didn't have time to talk about a new model that I came up with, but I mentioned some of the consequences of having non-invertible symmetries in the model, like what it can mean to the low energy physics of the model. In particular, it cannot be trivially gapped, but it could be gapless or gapped with non-trivial degeneracy. Now, there are some other generalization that one can work on. For example, you could ask if I've talked only about qubits in this talk, but you can ask there is a qubit version of this, and indeed there is a ZN version of ZX calculus, as I'm sure you're all familiar with. And I'm pretty sure that the ZX diagrams that I showed for the duality operator have a straightforward generalization to ZN. But you could also ask if there's a more general version of these things to Hopf algebras. And this is something that I'm interested in, but yeah, that's a question for the future. Another interesting question is understanding defects in this formalism. By defect, what I mean is local modification of the Hamiltonian that corresponds to symmetry operators that can be moved using unitary operators in a topological way. I have some ideas on how to think about this using ZX diagrams, but this is again something for the future. Thank you.
All right. Thank you very much, Pranay, for the nice talk.
Thank you.
Do we have any questions in the audience? Okay, so I was wondering, I think like a couple of slides back when you talked about the 3D plus 1D model, where you got this projector thing,
Oh, this one.
I think with your list of symmetries that you get at the end, I think a couple of slides later. Yeah, maybe this thing, yeah. So can I
Yeah,
also understand this as a projector onto the joint plus one eigenspace of certain Paulis?
that's right. Yeah, this is a projector. In fact, this slide makes it clear. This is the product of all projections onto states that preserve the loss law symmetries and also the one-form symmetries. That's exactly the point of this way of writing it.
Yeah. So I guess because like in stabilizer theory, like stabilizer codes, they work with the same kinds of like subspaces that are stabilized by the projector. Like,
Yeah,
is there any connection or anything like interesting to say? Can you say like, well, if you have a model with this kind of thing, then it defines a code in a certain way? Like, is there anything to say there?
I'm not sure about code, but I didn't have time to talk about this, but let me mention this model anyway. So there is this Hamiltonian model that I constructed where the first two terms are the lattice gauge theory and then a particular deformation. Now, let me go back. When h is equal to 1, we know that these two terms are exchanged and there is a duality symmetry. And for any lambda, this term maps back to itself. Like basically, this maps to a plaquette term here, and this maps to a link here, and that's also included in this sum. So this term is mapped back to itself. But anyway, the thing is, when h and lambda are equal to 1, you can write this Hamiltonian as a sum of projectors. This I don't think I have. Okay, if you have time, I can show exactly how this works. Uh, So here are some slides that I skipped. Yeah, in fact, it can be written as sum of projectors, where each projector is a product of two commuting projectors, where the PL is 1 minus XL, that's a projector, and Q is 1 minus product of these, that's another projector. And this L and P are chosen such that they meet orthogonally like this, so they don't have common support. So these two terms commute with each other in each term in the sum. So because it's product of commuting projectors, the product is also a projector. So we have a sum of projectors. But the Hamiltonian is not a commuting projector model. So because you have this kind of a term in the sum and this kind of a term in the sum, and let me play this slide. So, oh, sorry. Where was that? Yeah, these two terms don't commute with each other. So it's not a commuting projector model, but it is frustration free. And what that means is there are zero energy eigenstates. There are states in the kernel of this Hamiltonian, which means every term in the Hamiltonian each of those projectors should kill the ground states. And in fact, there are states like that. There are toric code ground states that are annihilated by this Hamiltonian, and there is a trivial product state that's annihilated by this Hamiltonian. And you can also show that there are no other ground states. Like in general, if you have this kind of a constraint, because in each term P and Q commute with each other, this constraint implies that either P kills the state or Q kills the state, or both of them kill the state. Now, the two kinds of states that I showed before, the toric code states, they are annihilated by all Q, but none of the P's. On the other hand, the product state that I showed before are annihilated by all P's, but none of the Q's. Now, you could ask if there is a state where in some region P's kill it and in some region Q's kill it, but there's no way you can do this in a consistent way on the boundary. So these are the only ground states. This is a nice feature of this model that you have toric code ground states and a trivial product state, which is a short range entangled state, whereas toric code ground states are long range entangled, as ground states of a single Hamiltonian on a tensor product Hilbert space. And in fact, this model, even though it's not a commuting projector, we can prove that it's gapped in the thermodynamic domain. This is a very non-trivial result. I don't know if there is an analog of this result in 3+1. I don't think anyone has proven something like this in 3+1 before. Like there are results like this in 1+1 dimensions and maybe in 2+1D, but I'm not familiar with anything like this in 3+1D. So this kind of relates to what you're hinting at, using stabilizers and some kind of ground states for those stabilizers. Like although this model is not commuting projector, you can actually find the ground state explicitly.
Could this non-commuting projectors be thought of as maybe like blockade codes, where where not all projectors are commuting at every time step.
Okay, I'm not familiar with plaquette code, so I don't know what to say. But oh, you mean at every instant it's a committing projector, but at different instances they don't commit with each other?
Like you don't have like it's like your stabilizer group is changing.
Yeah. So what you mean is like at a particular instant you have a commuting stabilizers, but at another instant you have commuting stabilizers, but these two sets don't necessarily commute with each other.
Yeah, it can
Yeah.
be thought of like that, I think.
So I think
Yeah.
so if you view like this kind of Hamiltonian thing as a code, you're looking at the ground state, and this is degenerate, and these different states in the ground state that are degenerate are the code words you have. And then what you have in the
Yeah.
plaquette code is you're continuously changing your stabilizers, and so that should change like your ground state. But I think in your
Okay.
case, you have at least one state that is in fact the ground state of all the things, even though they not commute. So then that means that like even though you're changing the ground state space, there's at least one state in there that continues to stay in there. Like I think that might then be kind of the connection there. But yeah, this is really
Okay.
not my field, so I might be saying completely wrong stuff here.
Okay.
Michael?
Hi. So this is a question which hopefully isn't unfair because it's kind of I know about some of this work about non-invertible symmetries via Sahan Sethnashri gave a talk at the University of Minnesota a few months back, so that's why I have it on my brain. And particularly sort of looking at that again, in that context, it was looking not at what's the word I'm looking for here? One moment while I get my brain back in order. Kramers-Vonnier duality, but transformation, but this Kennedy to what was it? Yeah, Kennedy to Saki
Yeah. Kennedy
transformation.
Tasaki. Yeah.
And I was curious if it seems like an obvious thing to sort of try to do sort of ZX calculus derivation of the duality the non-invertible symmetry for that. Has that been attempted?
Oh, you mean an MPO for Kennedy Tasaki transformation?
Yeah. Where it's
Yeah,
not
we know.
it's that ZXZ stuff.
Yeah. The KT transformation is well understood, right? Like it's just TST or STS.
Yeah.
Where S is the duality operator that I've been talking about. T is the entangler, the cluster entangler, and there is a ZX diagram for that. So you just compose them in that order, and you end up with a Kennedy Tasaki. So yeah.
Okay.
Yeah.
Okay. Do we have any other questions from the audience? Okay. Well, thanks very much, Pranay, for your talk and answering our questions. I think
Thank you.
one thing I sometimes ask for speakers if they're not like our usual crowd is, do you have any questions that you would want to ask people that know a lot about select calculus, like maybe things you're sort of looking into or want to know if they already exist or anything like that?
Oh, definitely one thing would be, is there a ZX calculus kind of thing for off algebras, or are people thinking about this? Because the natural, like everything that I've talked about is like an abelian internal symmetry and the Tambara-Yamadami category for that. But you could define Tambara-Yamadami for any finite group. It doesn't have to be abelian. So in that case, what would be the analog of all these ZX diagrams? That would be really helpful. And there are some couple of papers already in the literature, like one of them by Matt, my co-author on this paper. But I was wondering if anyone in this community is thinking about such generalizations.
So I know there is a paper by Sean Majid on quantum and braided select calculus, which I'll link in the chat, where they do try to like do ZXy stuff on more general Frobenius Hopf algebras.
Okay.
And maybe also this paper by Alex Couten and Sean Majid as well.
I see.
I think those might be the closest to what you're like looking at there.
I see. Yeah. Thanks. These are really helpful.
And definitely Alex Couten would be a good person to ask about this kind of stuff. He has thought both very long and hard about select calculus, and he has thought very hard about Hopf algebras. So
I see. Yeah, nice. Is there some universality or completeness kind of result for these things, or is that still
that I
being
don't know.
explored? Okay. I see. Yeah. Okay. Yeah. Thanks a lot for this references. I'm looking at that.